Not first row. Yeah, but ideally, I was never going to show this time.
Okay, we're live on YouTube, which makes us a step closer to be popular, I guess. A couple of announcements. I will have additional office hours today at 1 just to help everyone who needs help. Again, I was trying to help as much as I can on Piazza. Please see the TAs as well. They will have office hours today as well. I hope everyone will be fine, because maybe by now people do realize that the homework is not as hard as it looks like initially, or that there was a bunch of text which you had to read. But in the end, it's just like, maybe 100 lines of code. Okay, so hopefully everyone is fine with that, but talk to me if you need more help. Today, just a second ago, I was asked a question. So let's start with this. So today, let's start like this. So today our plan is to actually finish the interrupts and finish the system call implementation for the x86 kernel, right? In the x86 kernel. And what I mean by that is that, okay, we spent a couple of classes, right, on figuring out the hardware mechanism which allows the CPU to provide this idea of an interrupt, right? So we know that, okay, you might be running some code either in the kernel or in the user, and then suddenly maybe a timer, which is a physical device, raises some specific like pin, which is a connector for the CPU, right? And it says, okay, look, I want you to do something like like a certain amount of time has elapsed. So let's just react to this, maybe switch from one process to another. Maybe it's a network packet which showed up on a network interface, and the network interface says, okay, like I have a packet, so maybe you want to process it, right? So and at this point, the hardware allows you to say to the CPU to react to this. So instead of like fetching the next instruction pointer, which is ready in the pipeline, we switch to an alternative pass in the CPU. And the pass is very short. It just switches us to a different address, right? The address of the interrupt handler. And so this address, the interrupt handler starts executing, right? But the switch is a little bit involved. So what we have to do is a couple of values like instruction pointer, code segment, and ESPEflex register. They might be changed immediately during that hardware switch, right? So the hardware saves them on the stack. And if it happens that you have to change the privilege level, right, then you have to also, since you're switching to a new stack, because it's unsafe to continue executing on the old stack because user might attack the kernel and switch to a new stack segment, the hardware saves those as well on the new stack, right? So not on the one which you were running on like at privilege level 3 or maybe at privilege level 2, but you switch into privilege level 0, and the operating system will have a stack there for you to save these values, which will be always allocated and stuff like that, right? So we know this, right? And where we left last time was the point at which we said, okay, look, but we know the hardware mechanism, but really, how can we program the hardware to make anything meaningful out of it, right? Meaning, like how we set up the interrupt descriptor table, how do we set up the interrupt handlers, right? And this is where we were, right? And I actually was planning to answer your question, which you asked me, but let me just go with the interrupts, and then maybe later on, because it just logically makes sense to continue here. Okay, so we're looking at this code, and we started last time. Like this is our interrupt transition. Remember, timer interrupt, vector 32. The hardware says, okay, what I will start doing is that I will first look up, since it's entry 32, I will look up entry 32 in this table, which is called interrupt descriptor table. From there, I will read two values. I will read a value for the code segment, which will essentially will contain an index into the global descriptor table. And from there, we will potentially pick up a different code segment, descriptor for the code segment, meaning that the most important part here is that this privilege level might be 0. So if you were running at privilege level 3, right, in the user, this code segment, which says maybe like it's entry number 1, it chooses this entry here, and this one contains descriptor privilege level 0, which means that your current privilege level will switch from 3 to 0, and you switch from user to kernel, right? What you do as well is you read the address, which is called an offset of the handler itself, which sits somewhere in the memory of the kernel. And in x86, this entry point is called vector 32, because x86 generates those vectors for every interrupt, right? Those labels. However, if you need to change the stack, right, because you're switching from privilege level 3 to privilege level 0, the hardware will try to locate a specific kernel stack. And the pointer to this kernel stack will be inside another table, TSS. And if I remember correctly, the TSS itself is pointed by the entry in GDT. So I have to probably draw this line as well. So essentially, there is yet another segment similar to the code segment and data segment. There is something like task segment, right? And task segment is a number which points to the entry in the GDT, right? And this entry in the GDT says, okay, I know where the TSS is located in memory. And inside the TSS, hardware locates two new things: the new stack segment, which essentially picks this kernel data, which has privilege level 0, and the offset of the kernel stack, so essentially pointer to this stack, right? And at this point, it is ready to move on with the interrupt transition. So it says, okay, I will save these 5 entries on this new kernel stack segment, stack pointer, ESPEflex, code segment, code pointer, right? So essentially, this stack is a pointer to here, and this is like associated stack segment. ESPEflex might change, meaning that we can potentially might disable future interrupts, and this instruction pointer is an instruction pointer which was executing somewhere here inside the user process, right? And at this point, it says, okay, I got it. So I will set up the instruction pointer to point to the entry point of the vector 32, and we're ready to run inside the interrupt handler, right? So this is just a reminder, but everyone probably at this point, at least understands this at some level, right? And you will do the homework, and then it will become even more clear. Any questions about this transition? Let's just stop here for a second.
In additive, we are having address right, which will point to the one of the vector. Is that virtual address or physical?
It's a virtual address here. So it's a 32-bit virtual address.
So that means we will be applying paging and segmentation.
Correct. So segmentation and paging is always on. So this address, which we'll read from here, first we'll go through the segments, right? And that's why we first will fetch the new code segment from here with the new privilege level, saying, okay, can you really access this segment, right? And you need to configure it in such a manner that you can. And then the page table will translate from virtual to physical. You're right. Okay. Anything else? The only physical address. Okay, if I ask you a question, like on all these diagrams, there is one physical address. Which one? Everything else is virtual, or like logical, if you like, because it goes through segmentation. That's a good question. EAP. Okay, 1 bit is EAP. I hint no. Why EAP? Because EAP is just a regular address, like any other register, right?
The IDT.
IDT, well, closer, but no, not IDT. Because IDT, really, you can always translate. Yeah, IDT, you load the virtual address in the IDT-R register. Really, it's kind of, think of a chicken and egg problem. There's only one address which you cannot translate, because
Like CR3.
CR3, correct. Because really, you don't have a page table yet. It's like it's a loop, right? So you cannot say CR3 points to a virtual address, because in order to resolve this virtual address, you really need a page table. A page table is pointed by the CR3. So CR3 is really the only physical address. I'm pretty sure, I mean, don't quote me, I'm not like don't have absolute knowledge, but this is logical, right? So this is the only. So CR3 is physical. Agree? Okay, everything else is virtual because it gives you flexibility. The kernel can do anything. It doesn't have to distinguish between, you know, like IDT is physical or virtual, right? It's always, everything else is virtual, and that's useful. Okay, so now the question is like, we want to program this entry, vector 32. Let's just concentrate on this today. It's not as hard, but it's a little unusual because unless you've seen it, it's like, you know, higher whatever. Did you take any functional language programming classes yet? You know, when you see a purely functional language for the first time, it kind of like takes you for a spin. It's unusual, but this is also unusual, but much simpler actually. Okay, so the end goal is to jump into C because, you know, staying in assembly for too long, you will make mistakes. However, since C doesn't have abstraction of a register, we need to spend a little bit of time in assembly to make sure that we save everything what we need, right? And we already talked about it last time. So here, since we say, okay, we're not going to write the same code 256 times, right? We want to jump to a single function, which is called all traps. For that, we need to save which vector we entered through, right? And we say, okay, we save the number 32, right? Okay, cool. We will have it on a stack. Our stack will look something like that. So the hardware saves these 5 values, and sometimes the hardware saves this 6 value, right, for some interrupts. And I promise that I will figure out which ones, and I keep forgetting. I mean, it's not that important. Every time you write an interrupt handler, you will look it up, and you will know for sure whether it's saved by the hardware or it's saved by the hardware or not, right? And if not, then if we just simply save 32, then the layout of this data structure will be different. For some interrupts, there will be this entry error code, and for some, there will be not. And that's why for the interrupt handlers for which the hardware doesn't save this error code, we just push the error code, right? And I'll show you in a second which ones don't. Like, it's easy to check. And then the stack is always the same. It's easier. So you can say, in the end, I will come up with a C data structure which describes this stack, right? Not just these 7 values, but a little bit more. Again, we only saved those registers, those 5, right? Apparently there are more. We have general registers and we have some segment registers, right? And that's why this is what we start saving in all traps, because we want to restore them. And Asuk was the one who was asking, okay, what's going on with the data segment and the stack segment and everything? Okay, stack segment is saved by the hardware because we're immediately switching to an X stack. But the data segment is not, right? So, which means none of these instructions which we use in this code is actually a move instruction, uses a data segment, because we're still running on a data segment of the user code, right? So if we do a move instruction, we kind of screwed at this point, right? Because I'm guessing that the move instruction will be translated unless you like say move ss dot dot, not dot dot, but column and some address, right? Explicitly specify that go through this stack segment. I believe it worked, but I'm not sure. Not really sure, right? But all the pushes go through the stack segment, and the stack segment is set up by the hardware points in the kernel. Everything is fine, right? But now we say, okay, look, let's do this, right? So we will save all the segments on a stack, save all the general registers. And I talked about the push all instruction, right, which saves all the general registers in a specific format. And at this point, you say, look, by the way, we need to switch to the kernel data segment because we want to use move instructions, right? And we say, okay, well, we know that the kernel data is entry number 1 in a global descriptor table. So we shifted by 3 because that's the format, because the lowest 3 bits choose between local and global descriptor table. And these two specify a privilege level. And I don't know what it really means. And I admitted it last time and I still haven't figured it out yet. Okay, cool. But at this point, we initialize DS and ES segments with these 2 values, correct values of the kernel data, and we're good to go. As I was saying, our goal is to switch to a C function. And it's logical that we want to have this thing as an argument to this C function. So we have a C function which looks like trap and it takes a pointer to the data structure, which describes the layout of the stack, we want this pointer, right, as an argument, because then later on in C, we can access any register. So if we want to access a EAX register, we'll do something like, and this pointer is called TF, we'll do something like TF error EAX, right? Agree? And this will correctly land us on the part of the stack which saved EAX by this push all instruction. Agree? Again, we remember the calling convention and we say, okay, in order to pass this pointer, we need to push it on a stack, first argument, right? Right now, ESP register points to this data structure in memory. It's allocated on a stack, but it's fine. So ESP is pointing to it. So we push ESP itself, right? Meaning that we add ESP as an argument, which essentially points like this, right? Agree with this? And at this point, we can call trap, we'll land in C, and everything is fine. Agree with this? Okay, so a little bit of trickery, a little bit of stitching between assembly and C, but, and if you ask me a question, like how do we define this data structure, this one, struct, and I think it's called trap frame, it's kind of easy, right? So C is one of those languages which allows you, and it was designed specifically for that, it allows you to match layout of fields with the layout of hardware, right? So essentially, you can specify that if the struct goes in this order, fields go in this order, the compiler will not reorder them, right? And there are like sometimes there are corner cases, and sometimes you can give some directives to make sure that it doesn't happen. But anyway, so let's scroll a little bit forward. We have this. We call trap. We'll land on this trap function in C, right? And as you were guessing last time, there will be a switch, which essentially, remember, TF of this trap frame, this stack. Remember, we pushed the trap number. This is exactly when we did push 32. This is the number of the interrupt, right? Through which we entered, number of the vector. And in this specific case, this example shows you how you say, okay, if my trap number equals to 32, specifically like IRQ is number 32 plus timer is 0, so this equals to 32, we are processing a timer interrupt. And specifically what ESPEC is doing here, it acquires the lock, it increments ticks which count the number of interrupts since boot, so it's a notion of time in ESPEC. It tries to wake up all the processes which are waiting. So you can wait on a timer. You can say wait. Remember, there was a wait system call. You can say wait for 2 seconds, right? And it internally translates to wait on the sticks, right? And I'll show you how this wake up works later. And goes forward, right? There is a little bit of a additional logic here. I keep saying that maybe the kernel wants to switch to a different process, right? And I think I have it on the next slide. Okay, I don't, so let me just go to this one. When you want to switch at the end of this handler trap, so I skipped some lines here. You say if there is a process and the state of this current process is running, because maybe kernel end up without running any processes somehow accidentally, and the trap number is a timer, let's do a yield. And essentially internally inside the yield, you will switch, you will say, okay, this process is done running. So in ESPEC, each process runs for 1 tick, right? Every time the timer interrupts comes, the kernel will try to switch to the next process. And we will take a look at the implementation of this yield, but essentially it will save the state of the current process. We'll go to the queue of all the processes in the system. We'll pick the next process which has to run, and we'll restore the state in the registers, and we'll run that other process. And maybe like 10 ticks later, or maybe 20 ticks or 100 ticks later, the queue will go back to this process with another timer interrupts or another yield system call. And essentially, it will at some point come back out here, and it will continue in this function back in this process. Again, many ticks later, maybe all the processes in the system ran, and we came back to this one, and we'll continue in this function. I mean, we process the interrupt. At this point, our goal is to exit, right? So say we want to go back to the user code which was running. And not surprisingly, our kind of plan to do that is to restore all the register state and then do this magic IRET instruction, which will restore the last 5 things on the stack, which were saved by the hardware, and essentially resume running the user process as if nothing happened, right? Let me stop here for a second. So, and then I can finish the exit pause and explain how it works in details. But like, let's take a look at this code and see if we want to all understand the low-level logic of it, and to some degree, high-level logic and low-level implementation. Any questions? Good. Okay. So let's exit from the interrupt. This is where we enter, calling the trap. After that, okay, we start exiting. Not surprisingly, since we push this argument, we said, okay, restore the stack value, just restore the space which we use for this argument. And then we go through another function, which is called trap_rat. And this trap_rat, we actually fall through here. So just like essentially in this specific code, we just fall through, but there's a way to essentially jump to this target or call this target. Not surprisingly, we pop all because the stack is the same. We restore this argument, which we pushed on the stack here, right? Pop all is an instruction which is symmetric to push all. So it's essentially restores all the general registers. And then in the reverse order, we restore all the segment registers. This will contain now user values after we restore them. Again, we cannot do a move instruction here because it will try to use a user segment, most likely will fail. Since we saved the trap number and the error code on the stack, and each were 4 bytes, we will again restore the space on the stack by adding 8 bytes to the stack pointer. And at this point, we invoke the iret instruction. It's very similar to how we were exiting. Same iret instruction without restoring a privilege level. Very similar conceptually to how you return from a function. But the only difference is that iret, if you switch privilege levels, will restore these 5 values, which are currently on the stack, right? So if I remember the layout, it was stack segment, ESPEflex. Okay, this is it, right? So this is what we have on the stack, right? So we already restored all of it. Our ESP is pointing here, right? And the iret will recover this 5. Move these 5 values from stack to registers, right? Easy, at least intuitive, right? They agree? And at this point, we invoke the trap_rat. This is what the hardware is doing. Not surprising, it's the same, restore CS, EAP from this stack, EFlex, SS, and ESP, right? And at this point, we will be back. So this originally, we saved this instruction pointer, user instruction pointer. Now we restored it with iret. This stack is again empty, right? Because nothing is after iret. I mean, to be honest, it's a little tricky because ESP is currently pointing again here. So there is no such value as we didn't save anything on the stack. So next time we will enter with the interrupt, we'll again use this value, which will point at the very top of this kernel stack, right? But essentially we will continue like for the user, it looks like nothing has happened. If you are an attacker, you can say, I will measure time somehow, and I know that maybe half a second elapsed, and then you know I was interrupted. Or maybe it's a very quick interrupt, and maybe just like 2,000 cycles has passed. And you can measure that, yes, I was interrupted. My code was interrupted, but functionally, you continue running from this instruction pointer and continue with your program, right? Is that clear, this idea? That's how interrupts are handled by the operating system. And they are largely transparent to the user, to the program which was running. Any questions from about end-to-end story here? Good, everyone got the interrupts? Now, I mentioned, and you guessed actually a couple of lectures ago, that we can use interrupts to implement system calls. Why is that? Because we just seen that interrupts allow you to switch from current privilege level 3 to CPL 0, right? And while you immediately start thinking, okay, this is the mechanism which allows me to switch from user to kernel, and the kernel tightly controls the entry point, like this vector, whatever vector, some number, 64, for example. You say, why don't I will use int 64, which is hex 40, for implementing the system calls? Because the high-level idea of a system call is provide kind of like a library function invocation in the kernel, right? You cannot do, at user level, you cannot do call, I don't know, sys open, for example, and land on the kernel. Why? Because if you allow this, then you can, you can land on like sys open +5. And if you do some like checking of the arguments, maybe like checking what the user is trying to pass into the system call, those checks have to be executed, right? Otherwise, you have a security vulnerability, right? But if you do something like, instead of call sysopen, you say int x40, then you always land on this vector, and all this at some point you will say, okay, I'll just jump to the entry point of the system call, and all my security checks will always be in place, right? This idea is clear? Okay, cool. Let's take a look at how we can program it. You can randomly choose any of these numbers, right? So I said that 0 through 31 are reserved by Intel, then another 16 are IRQs reserved by devices, but the rest are open for you. And the only thing which you have to do, and I kept talking about it, is that normally you say, user cannot say anything like int some number here, because it's, again, security vulnerability, because it can pretend that the timer interrupt is delivered, or pretend that there is a non-maskable interrupt, right? If you allow it to execute int 2, for example. But you can configure the interrupt descriptor table in such a manner that this one vector, vector 64, is allowed, right? Remember, there is this privilege level, 2 bits, which define the privilege level in the IDT, right, for each of those entries. So essentially, if this is your IDT, one entry, entry 64, will contain here privilege level 3. The rest will contain 0, sorry, which means that only this one entry, only this one entry will be, sorry, like touching something. I think it just wants to move forward, because, okay, you got the point anyway, right? So x86 chooses int 64, Linux chooses int 128 or hex 80, right? It's just fine. You can choose any. You can choose whatever, 48 if you like. It's just fine. It's your design decision. Okay, let's take a look at how we build a system call on top of this, right? Same idea, same interrupt pass. So instead of vector 32, user will literally, this instruction which user invokes will be int x40, which is vector 64, right? And it's the same transition. So it's just that we land on a different entry here. So maybe vector 32 was somewhere over here. This has a different offset, vector 64, right? What do you think needs to happen next in this vector 64 if you want to execute a system call? Remember system calls, open, close, read, write. So what will you program there?
We need a parameter for system call.
We first need a parameter. So, if I would ask you a question, how would you organize system calls? Yeah, you can say, okay, we'll say each system call has a number, right? So, and then you can do like something like a switch on this syscall number. And then if it's like sys open, you will process the open, right? Sorry, click something again. And it takes, whatever reason, it takes longer to go back. It takes infinitely longer. I don't know why. Right, so it will be a switch and you will execute sys open here, right? And you say, look, but how will I pass this number? So what will be your logic? Because right now we said we have an entry point, which is int64. If we identify system calls as individual numbers, we need a way to pass them. So how would we do this? We can pick a register, and this is, I think, what ESPEflex does. We can either do the same calling convention. We can pass this number as an argument on a stack, on a user stack, and kind of follow the calling convention. But I think ESPEflex does use an EAX register as a syscall number, right? And essentially, we can reuse like the same entry pass, because remember, it was generic enough. It was saving everything, was jumping to trap, and logically, you can say inside the trap function, you can inside that switch, you say if it's an interrupt number 64, it means it's a syscall. So let's process a syscall, right? Like that's not surprising. Let's do it this way again. Same regular business. So vector 64, again, it doesn't push error code, so we push 0 here, we push number 64 here, we jump to all traps. This is how our stack looks like. I didn't update it. This is 64, this is 64. We go to this all trap function, save this segment registers, save all the general registers, set up the segments. There's a piece from an old x86 which uses per CPU segments, so this is no longer used. Then call trap again. Our stack looks like that. That's not surprising. And instead, inside the trap, we say, okay, if the interrupt was 64 equals to syscall, then it's a syscall, right? Okay, cool. There's a couple of checks. There's a killing a process. It turns out it's a little tricky. We'll talk about it, but okay. There's a check. If the process is suddenly killed, you kill a process, but you sometimes cannot terminate it right away because it's in some tricky state. Maybe it's waiting in a kernel on some kind of on the same ticks, for example, right? And then you have to exit from this ticks and we'll kill it later. So it will run for a little bit more. And then at this point, you force it to exit. If not, you say, okay, I will save the current trap frame parameter in the proc is the data structure which defines the currently running process. And then you start processing the syscall itself with the syscall function, right? So you enter the syscall function. Okay, let's take a look. So again, as you suggested, let's use the register EAX as a syscall number. So to distinguish which one we want to invoke, maybe it's a read, maybe it's exact, maybe something else, right? So all trap saves this EAX, right, on the stack as part of this push all instruction, right? So it's right there available for us. So this is what we're doing inside the syscall. We say, look, we know that this is a syscall number, so let's save it in a local variable num and start processing, right? We have to do a little bit of a security checks here, because at this point, right, this EAX value is passed by the user. This is the first time we start thinking about, I mean, we were thinking about security all way long, right? Because we said, okay, we'll create a very specific page table, very specific global descriptor table in such a way that we can place the user process in a tightly controlled environment, right? Which is controlled by the kernel. And this is the interface from that environment back into the kernel. So we have to be careful here because the user can pass anything here. So it can be OX, FF, all Fs here, right? For example. And if we keep system calls as a table and use this number as an index in the table, then it's a, out of bounds access, right? So that's why the kernel says, okay, by the way, I think it's a signed integer. So I will make sure that the number is greater than 0 and smaller than the number of the system calls, which is defined in the system, right? And actually the system call in a table, maybe the table can have gaps for whatever reason. Maybe some system calls, we decided to unregister them or something. And we say, okay, the system call is present, right? If not, we say unknown system call, process ID, process name, yada, 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 and we will return -1 as the return value, saying, okay, you failed executing the system call. We don't kill the process, but you can at this point. Why not, right? You got the point about the checks, right? Okay, but if everything is fine, x86, instead of doing a giant switch, and it's just it's a preference, it's a style of how you code those things, we'll have an array of system calls, right? Meaning array of function pointers. And I hope you understand that you can define it in C. This is how you do it. You say, look, this is the syntax. So it's an array of function pointers. This is a pointer. This is a function because it has a void type. And this is array. And this is a definition for all the system calls. And you specifically define these values, like maybe 0, maybe 1, right? Maybe there will be gaps, right? So when I will ask you maybe tomorrow to extend x6 with a new system call, this is where you will stick your own entry, whatever, your foo bar here, right? In this table. And do your sys foo bar implementation of your system call. And don't forget to change the number of system calls in the system because you extended it by 1, right? So because if this is like 255, then you have to make sure that number of elements in this table or like number of defined system calls matches, right? Good? But this is the table. So when this, understand that if we invoke an entry in this table, we invoke in a function, right? Clear? Okay. So like kernel starts processing it, right? Now we kind of, and it's like, it's obvious. We'll talk a little bit in a second about how you pass arguments because those functions are actually void functions, right? So there is no, remember, read, for example, takes what arguments? Do you remember? File descriptor. I think buffer goes first and then size, right? So those arguments are not yet present, right? They are nowhere around. We'll discuss how we pass those arguments in a second. I'll make a hint here. So they are saved on the user stack, right? So because it's a calling convention, we'll just fetch them from there. Give me a second. So, but again, so the question is the following. So how does the user program access the system calls? And you can say, you can do this, but it's a little bit odd if you say, look, I will in the end have to call the int instruction from my lovely main function with a syscall number passed inside EAX register, right? And maybe some arguments passed on the stack, right? So this is exactly what happens, but you want some kind of a syntactic sugar around it to make sure that you don't have to write this every time. So if I would ask you to, okay, can you come up with some kind of a technique to make sure that you as a user have a nice interface, which goes something like sys or whatever, like exec with some arguments here, right? But internally, the assembly has this code. So how would you do that in C? Or in any other language?
You can create a library of stubs that can be called from C, and each one of those then.
Correct. So you can say, okay, I'll create a library where I will define exec as this, right? It may be an assembly library, just exported symbol, totally fine. We can do a step better and say, okay, since all of them look the same or almost the same, right? We will just generate them automatically, right? With a collection of macros. So on the user side, so this is user.h. It's actually the very first time in this class where we're looking at a file which is part of the user code. Everything else before that was a kernel, right? Every header, every assembly file, every C file was part of the kernel. But this user is what your main function when you do something like cat and you have a main function. So you will say include, and you will include this user.h, right? This definitions of this on the function calls, right? So an exec will be here, right? Okay, we got it. But now we need those stubs which you suggested, right? So because like for example, part of this stub will be generated by the compiler itself, right? So for example, if you say, I want to invoke a write system call, from that definition of the write system call, the compiler knows that you have 3 arguments, right? Integer, which is file descriptor, pointer to a buffer, and another integer size, right? The compiler knows how to generate a call side. It will generate something like, okay, in the end, I will call a write. Remember, linking and loading. Write will not be yet resolved, right? So it will be like undefined symbol, but we will link against the stub. But the compiler knows that, okay, if you want to push 1 as a file descriptor, you push it as the argument here, pointer to a buffer, push a pointer to a buffer, and EBX contains this value, right? So this is what the compiler will generate. But still, we don't have this. We need this stub for this write function, right? This is where the int 64 will be actually sitting. And those things will generate as assembly macros, right? Just a heads up, compilers can generate slightly different code depending on the version. So in the first version, compiler was using a push. Here we're just using move instructions, right, to accomplish the same. Like this is at the very top of the stack. This is stack plus 4. This is stack plus 8. I'm using AT&T syntax here, right? But again, so let's finally take a look at how we generate this. So there is a way, and we've seen it before, that assembly has macros, right? And essentially this uses user system.s is a library, essentially, which implements all the system calls with a single macro, which defines a syscall. So it takes name, something like write, and generates this code, where it replaces this name with the write. So it's a global symbol, write, and the label write. And essentially what it does here, it says, okay, but the write name, this is concatenation. So it will be sys_write, which is a number. We'll move it in the EAX register and invoke a tsyscall interrupt, right? And that's essentially if you generate them for all, and when you're doing your homework, so you will say syscall foobar here, making sure that this stop is generated, right? And make sure that you add something to this user.h file as well, right? Okay, clear? And this will, a different object file, which will be uses.o. It will get linked with your main or whatever you are doing, cat.o, right? So here, this this label sys write was not defined, but it's defined in the uses.o, right? Remember, linking and boarding. Okay, so any questions about it? And in Linux systems, it's typically done by a library which is called libc, which provides those system calls, and essentially everything is there sitting inside. The tooling might be slightly different, but in the end, it's conceptually similar. Okay, cool. We know how system calls work. So, for example, just to give you a concrete example for this, if you really look at the disassembly of the cat program, right? This is what the write label will look like. It will push this number, which is 16, into the EAX register, and there will be an int x40 interrupt, which invokes the interrupt system call. Good? Okay. Let's take a look at the very last thing. So system call arguments. Remember, we defined the table. Every system call is a void function. The question is how do we pass arguments? I said that they are where? They are on a stack, on the user stack. Okay, so how do you think we can access them from the kernel? We have a kernel stack, yeah. So this ESP value here will point us to the user stack, right? Somewhere here. This is kernel, and this is user, right? Good? And the arguments will be where? They will be up from this ESP, because remember, and there will be specific layout. So we push the, there will be a return address, which we pushed while calling this label. But up above, there will be arguments, right? Okay, so we'll build a helper function in a kernel, which allows us to fetch those arguments. And since we don't trust the user, so if user passes us a pointer to a buffer, for example, as one of the arguments, what do we have to do? We have to validate those arguments. We have to say, okay, this pointer is really a legit user pointer. How do you think we're going to do this? What are the conditions we have to check? What is the user? What is the definition of a user?
It must be within the user's address range.
Correct. And in order to make sure that we are within the user address range, we will maintain a specific variable which tells us how much memory user has allocated, right? It will be called proc.size, or like we'll typically will access it as proc error sz, right? This is the size of the user address space. Okay, let's take a look. Again, so inside sys, right, inside the kernel, we're back in the kernel, which was invoked like this from the user, right? We say, okay, we will have a helper functions which say we will validate a file descriptor, and for the argument 0, we will validate the size of the buffer, which is n here, as the second argument. So this one, this is 0, 1, and 2. And we also will validate the pointer, this p, against this size. So the condition for the pointer is not just that the pointer is within the user range, but also that the entire buffer is within the user, right? So because the attacker can manipulate and say, okay, the size is so large that it might spill into the kernel range, right? So, and like we will have separate functions, some to validate the pointers, some to validate the integers, and some to validate the file descriptors, right? Because if we say, okay, if it's a file descriptor, we're going to check that it's really an open file descriptor, not some bogus value which the user tries to process, because that it can also lead to an attack. And then we can invoke a real implementation of the system call, something like a file write, which will take this f, a pointer to the file data structure, which is returned by this function here, the pointer to the buffer, which we validated, and you say, look, this is the valid pointer p, and the pointer to the size, which we validated and got from this argin function, right? At this point, it's all safe. We know that those arguments are safe. We enter the kernel and perform the write, right? Let's take a look at those functions, right? So first, if you say fetch the nth argument as the integer, we'll generate a fetch function, right? And fetch reads the memory of the user, right? And as you were saying, so it's we know the location of the user stack. It's part of the stack of the trap frame ESP register. And since it's nth argument, right? Each argument is 4 bytes. And since there is a return value, we skip over this return value. That's why we add 4 here, right? And what we want is we want this value returned as this integer pointer argument here. The fetch itself, what it does is the following. It says, okay, the address you're trying to fetch, which is this address, which is this user level stack plus 4 multiplied by n, is it really within the range of the user memory starting from 0 to something like proc size? And by the way, since the whole thing is an integer, it might be crossing this boundary. That's why we're going to check as well if address plus 4 is also within the range, right? If not, we return -1. If yes, we just say, okay, read this value, or like set the pointer to this value. Agree? Easy? Well, again, you will have to do it for your own system call. Just make sure that you follow.
We are not using EBP pointer, right? So it will be different to traverse arguments on the user standpoint. If we use just only ESP, then it will be, how do we know how many arguments we pass?
Yeah, remember, EBP works nice for local variables, because if we, in this specific case, ESP doesn't change, right? So everything above it is well defined, because this ESP will be the same throughout the invocation of a system call, right? So, and it's always 4 plus 4 multiplied by n to get the argument, right?
But we don't know how many local variables are allocated. ESP will be fine.
We don't care, because look, because we know, in fact, the stub which we implemented doesn't even maintain the frame, right? We just skipped it just for performance reasons. But we know that the layout for each of the stubs, the layout of the stack is the following: user stack, the return address, and then the arguments, arg1, arg2, arg3, right? And ESP is pointing right here, right to this value. And so we say +4 lands us on like red, and +4 multiplied by 1 lands us on the first argument. So you don't really need ESP. The user ESP will not change. We saved it in a trap frame, and we'll always have it, right? Agree? Okay. Okay, so fetch, like again, the high level point here is to make sure that we do the checks because the user might abuse us. And this is valuable because even if you program a web server, the user might just like, you will have similar set of problems. You know, the user might pass some identifier which locates some state of your session inside the web server, and you have to validate those arguments, making sure that okay, this session really belongs to this user, and this is what we're trying to do. Okay, so we've done this. This is my explanation for each argument. We do this fetch. Remember, like I just wanted to explain the meaning of this proc as z variable, right? So when next time we're going to be looking at how we create a process, and every time we load a section, we increment as z. We load text section, then we load data as z becomes here. We set up the guard page to make sure that the user cannot overflow the stack as z will be here. Then the process stack as z will be here. And this is the initial thing when the process starts running. But as the process moves forward, it might use SBRK system call to allocate additional memory on a heap, process heap. And this is why the proc as z eventually will start pointing here. But all of this memory is a user memory, and it also mapped. ESPEflex has a guarantee that those pages are always mapped, present in the page table, so it's always safe, and it's the same page table. Remember, I was telling you that it's much faster to execute the system call on the same page table instead of switching it, because when you land it in the kernel somewhere here, right, and you're trying to read any of the user addresses which are passed to you, it's just a regular read of a pointer, right? Because those pages, this memory is on the same page table, right? This argument is clear? Somewhat. Okay, cool. Well, yeah, emphasize it was a homework. Everything will become crystal crisp in next week. Okay, cool. So we know process size, right? So if we want to validate the buffer, we first say, okay, we will validate the size here, right? And then we will validate a pointer to a buffer. It's a gate. So when we validate a pointer itself, we say here's the pointer to a pointer, and here's the size. So okay, this is a number of an argument, and we do those checks, right? So essentially, we make sure that the entire buffer belongs to the user. That seems correct to me. Okay, cool. So this is where we actually end system calls, right? So we learn how the system calls work, right? Agree? So it thinks like a small step, but it's kind of a huge gap, a huge leap forward, because now you say that we boot it into main, we know how to program the kernel, and we don't know yet how to start the user processes, right? But we will learn it maybe like on Tuesday, right? But we also know how to invoke the kernel from the user, right? So, and just as an illustration, I wanted to spend some time talking about how, for example, something like a print on a console works, right? So the console is a very simple device driver. So it's as simple as it gets, right? So it typically gets 1 byte with it, which is a character which you want to print, right? But essentially, let's first take a look at like really this. It's also part of your homework somewhat, right? So I used a similar implementation inside my Hello World homework, right? So something I call it kprint or printk, right? So, but it's a printf function here, right? Which the kernel invokes specifically to let you know that a specific CPU number has started, right? So it takes a CPU number and essentially takes the number itself and formats the string, outputs something on a string on a screen. So let me just show you real quick how it looks. So this probably is a good. We go to ESPEflex public and we say make PMU Nox, so it will start booting, and it boots with 2 CPUs. I have some debugging prints here, but this is the printf which we have on the screen. So booted started CPU 1 and CPU 0, right? Okay, let's take a look at how it's implemented. So, by the way, so does anyone have a guess for how to implement a printf function? What should be inside?
We have writing to BIOS memory public address.
Right, so like we remember how we did hello world print on the screen. And this will be the very low end of this device driver, which will put something on in a memory buffer, right? Which like HELLO, right? But here, what we need to support some kind of a string formatting, meaning that there is a new line string here. There is this number which we pass as an argument, right? So how do we go about it? How do we build this function? Essentially, remember, when you build a kernel, there are no libc libraries. There are no standard libraries from the C ecosystem. You can link against them if you manage, and it's possible for some of them, right? So, but really, there is nothing. You have to build it your own. So if you want to printf, you have to build it in ESPEflex, and ESPEflex builds its own implementation of printf, which is not super sophisticated, but simple one. That's why it's useful for us. We can quickly look it up. So who can tell me?
After handling the slash and I use 18 that is the text mode, but 18 to 25. So we have to move to the next line of the cursor, right?
Correct. So essentially, what you need to do internally, you have to implement a minimal parser, which parses this string, figures out, for example, new lines, figures out references to like numbers and pointers, and essentially replace them and print out something what is passed here in place. So for example here, so what is happening here, this is this parser. So essentially it says, okay, I will have a loop, right? Starting from the beginning of the format string, going to the end. And for example, if I see something like, what is it reading here? So it says, okay, if it's just a simple character, so it's not this special character which defines the formatting, I will just put it on the console with a specific console puts of this character function, and we'll go to the next iteration of a loop. However, if I do detect some formatting, I will try to read the next symbol, right? And then depending on this next symbol, so for example, if I'm passing something like say I'm passing a string, so here case S, I will essentially be printing this. I will get this argument as a string here, and I will be implementing a for loop, outputting this string one by one on the screen, right? Is that clear, this logic? Okay, but let's take a look at how this putc function works, right? So this is the first example of a simple device driver. So it says, okay, the kernel implements a simple function which can put one character on the screen. This character can be a little bit special. So for example, it might be a backspace, and then you put a magic sequence here, or it can be a regular character, and then you just use a uart put C on this, like, which really puts a character on the serial line. And this uart, remember, it's somewhat similar to a disk driver. It follows a specific protocol. Again, remember, I was telling you that the way to communicate with external devices, with some of them, is through those in and out instructions, which essentially allow you to read something and write something into a collection of ports, which x86 was implementing as an abstraction of the device driver. So later on, it kind of like turned out to be too limited, just because we have a very limited number of ports, and the hardware ecosystem was growing so fast that, you know, they added like memory mapped devices where you just write into a specific region of memory. But what you're doing here is that you say essentially you follow this protocol of writing in a specific port of a COM1, communication interface 1, just essentially just reading the value, making sure that it's in a ready state, doing some micro delay here, and eventually outputting this character into this port, right? And this is how it shows up on the serial line, which is implemented by QEMU. And if it's in a data center, there will be a physical cable connecting you somewhere. This essentially, the signal will show up on the serial line, right? So, okay, we got it. So this is how we implement the printf, for example, in a kernel. What I want to do. So we're printing one character on a line. Where is that? I wanted to emphasize that, by the way, there's another function here which uses a CGA interface, and the CGA is essentially the frame buffer. This is where you were actually printing hello in your homework. So what ESPEflex does is when it says print on a console, it prints in two places. It prints on a serial line. So like essentially like this serial line interface, which is implemented in a cable, and you can attach an interface of like this, the other end of this cable you can attach to your own machine and essentially read what essentially this end writes, right? So this is this COM interface, right? Serial line, and this is what we're using in QEMU as well. And the CGA is essentially the same character gets printed both on the VGA and CGA. So I mean on the serial line and CGA output, right? So CGA is really a screen of your machine. So essentially, if you're booting ESPEflex on a laptop, so this hello will show up here on the screen, right? And the code for this CGA function is very similar, right? So essentially, it follows a slightly different protocol. So it's a CGA put C. It essentially keeps track of where you are in this frame buffer, because if you say I have a screen which has like maybe 40 lines and 80 characters here, so if you start printing H, 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 and so on, at some point you reach the end of it, right? At this point you say, look, I, by the way, have to like change my position. So this is like scrolling and stuff, right? And your next H shows up here, right? So you have to implement those abstractions of scrolling, abstractions of overflowing the line, right? But in the end, if you read this code, you will understand what's going on. And in the end, everything boils down to essentially a memory copy to a specific location in a frame buffer. So you compute all these values, you handle the scrolling, handle everything, but in the end, it's just like instead of like using this in and out interface, you just copy this character in a buffer. Very similar to how you did it in your homework, but now it's just like a more sophisticated interface, right? Any questions about this? So this is the very simple device driver. And ESPEflex also has a device driver for handling the keyboard. So how do you think keyboard is implemented? What happens when I press a key on my keyboard? Which one? It sends an interrupt, exactly. So it actually does send an interrupt. And you can take a look, like read through the source code of ESPEflex. It does send an interrupt, and there is an interrupt handler which handles it and reads reads the value from a port, which says, okay, yeah, you pressed H, for example. So not surprising. So now you kind of know, and I mean, like we didn't talk yet about complicated device. We touched on this a little, but this is the two very simple devices, or three if you like. So a serial line, a CGA, so which allow you to implement output, right, and read something from your system, and a keyboard driver, which essentially sends an interrupt, and you can, in your interrupt handler, you can read the character and says, okay, he pressed or she pressed H, for example, right? Okay, this is useful. So we understood essentially how we boot into main, how we implement system calls, and how we essentially can handle simple interrupts and why we need them, right? It's not yet the end. So ready for questions. Everyone is slightly tired, I can see, but all good, interrupts are there. Okay, and now let me answer a question, so which I was asked in the beginning of the class, and I decided it's a good question for everyone, right? Essentially everyone who is in the class. So the question was like that. So when you are inside QEMU and you do something like info mem or even info TLB, right? How does it really work? Does anyone know the answer? what is going on? How does the QEMU knows your mappings inside ESPEFlex? Because it's one of the ways to check that you did the mappings correctly, right? No, I can illustrate with an example since we still have like 10 minutes. I was here. It was someone's homework. Someone sent it to me. I debugged it. I was make QEMU Nox, for example. Wait, pardon, that's wrong. Let's do it again. GDB. Oh. Attached to the GDB, there are GDB here, breakpoint on the start, continue, right? Layout, as in just to check that we're there, right? Everything same as you are doing. Info TLB says page tables are disabled. Info mem, page tables are disabled, right? So if I do another breakpoint, something like breakpoint on main, and in this specific implementation, I think some page tables are set up, maybe they are not set up, then we will never get to main, which is likely, but let's take a look. So now we have info TLB. Wow, there's a lot, right? So how does QEMU implement this? And it says, okay, oh, it actually says, okay, cool. Yeah, everything is mapped from 0 to 4 MBs, right? Say again? Yeah, in boot.asm, we do set up a page table. I just said it's not my implementation, it's someone, so I don't really know what it is. I was helping to get to some point to that student. Okay, the question is like, how do we, do we first understand what QEMU is? What does QEMU do? And what is, if I ask you to write QEMU, can you? What if I pay you money? A lot of money. I can, everyone can, right? I always said sir yes as well to all the funding agencies which support me. But yeah.
Maybe like a guess, it just like has its own virtual memory that it's remapping and pretending that it's a physical memory.
At a high level, yes. Let me just draw you a picture. So what QEMU is, it's just a regular, regular program, which this guy, and I keep forgetting his full name, but his first name is Fabrice, I think Bellard. Like, okay, we can quickly look him up just for the fairness. Fabrice, yeah, Fabrice Bellard. So he built it like as a hobby, actually, as a side project. It's not even his main job, which is kind of fun, right? So he says, okay, I wanted to run some programs on an emulated hardware. For example, I want to run a MIPS CPU on my laptop, which is x86, or I want to run ARM programs on my x86. He says, okay, sure, I will start like you would start. I will like main function. Like I'll do a little bit of a malloc here and say that will be my memory. So essentially, I will allocate memory, and I will pretend that this is memory of my physical system. Let's say 256 megabytes, like we use in QEMU, right? Then he says, okay, look, I will start following the protocol. It's a little bit hard when you have a bias, so let's just skip a bias for a second, but he does the bias. And you say, look, I know that, like, remember how execution starts, so I have to read 512 bytes. Sorry, there's this. I reached the end of it, and it deleted everything. But don't worry, we'll come back to it. So slideshow, start from. So again, let me recover from my Mr. Actually, I don't have to draw here because I don't like this drawing environment, but I can draw here. Bear with me for a sec. Where is it? Here. So he says, okay, this is my main function. I said I will allocate some memory with a malloc. I'm running on Linux, for example. This memory will be, I will pretend that this memory is my physical memory from 0 to 156, physical memory of a system I'm emulating. I know that I have to read 512 bytes from disk to follow the boot protocol and put it where? To this magical address, which is 0x7C00, I think, right? And then what? And then I say, wow, and then I will do like a for loop forever, which says, okay, like I will set the instruction, I will maintain like a structure of a CPU, for example. I will have a struct CPU, which will have instruction pointer, will have EAX register and all the other registers, and I will set EAP to point to this address, right? And I will implement it as a fetch of a memory from this address. I will say this is instruction. I will decode this instruction. Decode meaning I understand how x86 or ARM encodes instructions, and I will decode them in software, right? And I will maybe do something with it, like decoded instruction, and then I will execute. And this execute of this instruction will essentially somehow change my state of this CPU, which I'm maintaining, right? Clear? So he says, okay, look, I need the disk. So how will we represent the disk? With a file in a file system. So he will just do like fopen over disk image, for example, file, and then we'll be doing a read from it, like from 0, we'll read 5, whatever, into the buffer, we'll read 512, right? So copy it here, right? And then this loop goes on, and essentially, if your fetch, decode, execute loop faithfully mimics the logic of the x86 or any other CPU, your state will be evolving according to what's going on here, right? Agree? What happens, for example, when this guy tries to do like in a port, because like, I don't know, some port number XXX, right? It tries to read the disk, like our bootloader was trying to read the disk. What do you think you have to do in this case? How do you emulate it?
You should have a directory that is like representing the disk, or?
You know, like our disk is the file. What you have to do is that you need to understand the logic of this in instructions. So you might have to like say, okay, I will have maintain some kind of an array of ports, and for each port I will like emulation handler, which emulates in and emulates out, right? And of course you say, look, I might not handle all the ports because there are hundreds of them, different hardware, but I will handle some subset of them. I will clearly want to handle console, maybe VGA, maybe disk. And disk is a reasonably simple protocol. This what is it called? SATA, and before SATA it was IDE, right? IDE protocol, he reads the manual and he says, okay, when you read a port, I don't know, let's say 128, the IDA specification says that the disk will do this and this. And then maybe it will read like, do some micro delay, read this port, and like some in repetitively waiting for the disk to get ready. And at some point it says, okay, like, yeah, it reads the value from like block number, I don't know, maybe block number 1, which is address 512. And he just emulates it faithfully. And you say, look, it reads it in a port, so I will read this 4 bytes of this sector and put it in that port and return. If this is an in instruction here, I will faithfully emulate it, right? Essentially like putting this value into the register, which instruction is using as an argument, right? Agree? And okay, if it goes on and on and on, it actually runs, right? x86 is quite complicated, but if I ask you to emulate something like ARM, not even ARM, something like MIPS, which I, for example, use in my computer organization class, you really can take a textbook, this Hennessy-Patterson textbook. The instructions fit on 1 page. Like there's like additional extensions, loading points. We say, okay, we're not going to emulate those, but we're going to emulate those tiny subset, like literally like maybe 30 to 60 instructions. You can do it as a homework. And this is what he did, right? So, but he then kept extending it, and at some point it's a faithful implementation of x86, right? Agree? It's might be slow. There are ways to optimize it, but okay. If it's slow and you're fine with that, that's totally fine. This is called an emulator. This is what's running inside QEMU. Okay, now when we say info TLB, what happens, do you think? Or info mem? Let's say info TLB. A little bit simpler.
What is that like?
What does it do?
Yeah, that's it.
info TLB, I think it dumps all the mapped memory. Let me just, yeah, info TLB says, I will dump all the TLB entries. Like it would be nice. As I said, it's not Corey who built it. I get confused. So it's another guy from Utah, Austin Clements, I think. Yeah, if you can look through the patches and like figure it out, but that was him. Sorry. So that's why my boot was taking so long, because this thing was instantiating that many TLBs, right? So that many TLB entries. Let's get to the first one. So the first one is here. So it says, okay, look, looks like to me that the physical address at address 0 is mapped, sorry, virtual 0 is mapped to physical 0 with permissions writable. It allows you to debug your homework, saying, okay, like, did I set up my page table correctly? If you screw it up, then, you know. So what do you think you do inside QEMU? Or like, what did Clements, Austin Clements did? To extend, how did he hack QEMU? Okay, there's, yeah, I forgot. I saw your hand. I'm sorry, I didn't react. Exactly. So what he does here in QEMU, he says, okay, in my CPU, there will be a CR3. I know that it has a pointer to the physical address in memory, right? He goes here and says, okay, what's the first entry? Is it present? If it's present, then let's go use this physical address to go to this leaf, to this leaf. Check if this entry is, so this is a page table directory. This is a page table. If this one is present, and there will be a physical address here, and this is the mapping. So this entry 0, which means that this is address 0 and 0, and whatever, the offset is 0 as well, mapped to this physical address, whatever, XXX, right? That's what he does. And then in a loop, he walks the entire page table and dumps it for you, right? So it's not super hard. I mean, I leverage this question specifically to explain to you what QEMU is doing, because this knowledge is kind of more important than just, you know, simply understanding of info TLB. But that's what's inside QEMU. And the way you approach it, and like I literally will take just a minute. If you open up the that's what I did when I was a student. So QEMU, GitHub, maybe it wasn't on the GitHub back then. If you go here, what is this? It's not even the original QEMU.
Use a G instead of a Q.
Yeah. G stands for genius. Yeah. So you start looking at those files, you quickly get lost, because I mean, it grew up to be giant. It supports multiple architectures, but this is the trick. So you go and navigate back in history, which is a little harder on this, but if you check it out correctly, so we go to some very, 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 very early version, which I might not have, but I did it somehow, maybe not on GitHub, so I use command line interface. Essentially, you land on one of the early versions when the code is still really simple and readable. So you can do the same with Linux kernel. It doesn't work that well because it was messier back then than now. Now they cleaned it up. So the first version which Linus came up with was like really hardcore. So he like a little was probably my kind of quality of a programmer. So you can do much better as a community. But the same with Fabrice. But no, for Fabrice it looks better. So if you go to one of the early versions, it's very clean, and you like literally what I explained here, you can read it in his main function. So just again, a trick which will help you to understand how big and complicated software runs. So same trick can be done with Nginx, Apache, web server, stuff like that. Okay, good, thank you. So for now, and I will meet you on Tuesday to explain how we create the process.